In the context of 4D Einstein Gauss-Bonnet gravity, this research investigates the stellar structure of quark stars using a novel interacting quark-matter equation of state. By modifying the Tolman-Oppenheimer-Volkoff equations to accommodate the 4D EGB gravity framework, the study examines quark star mass radius profiles. The results show that increasing the Gauss-Bonnet coupling constant alpha or the interaction parameter lambda leads to an increase in the mass radius profiles of quark stars, enabling larger quark stars to be supported at a given central pressure. Conversely, when lambda less than 0, the interaction effects diminish the masses and radii of quark stars. Analytically, a critical central pressure is identified, below which no quark star solutions exist due to the pressure function having no roots. Notably, quark stars can exist below the general relativistic Buchdahl bound and Schwarzschild radius r equals 2m, as the 4D EGB theory lacks a mass gap between black holes and compact stars. Even with small alpha values within current observational constraints, quark star solutions in this theory can describe extreme compact objects, ECOs, whose radii are smaller than those allowed by general relativity. The use of a unified interacting equation of state in 4D EGB gravity provides a novel framework for understanding quark star structure and behavior. The results of this study have significant implications for our understanding of compact objects and the potential for 4D EGB gravity to provide an alternative to Einstein's general theory of relativity. Modified theories of gravity, particularly higher curvature theories, continue to attract attention due to their potential to address issues in modern cosmology, quantize gravity, eliminate singularities, and provide viable competitors to test general relativity. Higher curvature theories modify the linear relationship between curvature and stress energy in general relativity, replacing it with an arbitrary sum of powers of the curvature tensor. Lovelock theories, a type of higher curvature theory, have been at the forefront, possessing second-order differential equations of motion. However, their physical significance has been unclear due to higher-order terms contributing to the equations of motion only in more than 4 spacetime dimensions. The quadratic case, known as Einstein Gauss-Bonnet gravity, has recently circumvented this restriction. The Gauss-Bonnet contribution to the gravitational action is given by equation 1, which becomes a total derivative in 4 dimensions and thus cannot contribute to a system's gravitational dynamics. However, it was noted that several exact solutions to dimensional Einstein Gauss-Bonnet gravity have a sensible limit under the rescaling of the Gauss-Bonnet coupling constant, as shown in equation 2. This approach has led to the derivation of various 4-dimensional metrics, including cosmological, spherical black hole, collapsing, star-like, and radiating metrics, each carrying imprints of the quadratic curvature effects of their d greater than 4 counterparts. In the realm of theoretical physics, a novel approach has emerged to describe compact astrophysical objects such as neutron stars and quark stars. This method leverages 4D Einstein Gauss-Bonnet gravity, which is derived from the Gauss-Bonnet term in higher dimensions. This term can be used to obtain a 4D scalar tensor theory, a specific type of Horndeski theory. The action for 4D Einstein Gauss-Bonnet gravity is presented, showcasing its potential as a phenomenological competitor to general relativity. This theory holds significant interest due to its ability to provide an alternative framework for understanding the behavior of compact objects. Compact objects are of paramount importance in modern astrophysics, particularly in light of recent gravitational wave observations. These objects, which include neutron stars and black holes, are extreme environments where the laws of physics are pushed to their limits. To accurately describe these phenomena, theories must be developed that can capture their complex behavior. The application of 4D Einstein Gauss-Bonnet gravity to compact objects offers a promising avenue for exploration. By utilizing this framework, researchers may gain new insights into the structure and evolution of these enigmatic objects. Furthermore, this approach could potentially shed light on the nature of dark matter and dark energy, 2 of the most elusive components of the universe. While this new perspective holds great promise, it is not without its challenges. The mathematical complexity of the theory requires careful handling, and the precise nature of the scalar field involved remains uncertain. Additionally, the theory's compatibility with existing experimental data must be thoroughly tested. Despite these hurdles, the prospect of utilizing 4D Einstein Gauss-Bonnet gravity to understand compact objects presents an exciting opportunity for advancement in our understanding of the universe. As researchers continue to delve deeper into the intricacies of this theory, they may uncover novel insights that challenge our current understanding of spacetime and gravity. The research focuses on quark stars within the 4DEGB theory, utilizing a unified, interacting quark matter equation of state. A novel aspect is the consideration of a single parameter lambda to characterize strong interaction effects, including perturbative QCD, color superconductivity, and the strange quark mass. The study solves the modified TOV equations for various combinations of Gauss-Bonnet coupling and QM interaction strengths, constrained by observational limits. The results show that quark stars in 4DEGB can be extreme compact objects, ECOs, with radii smaller than those allowed by the Bookdahl bound in GR. This includes quark stars whose radii are smaller than those of corresponding black holes in GR, indicating a new class of astrophysical phenomena. The study also derives a critical central pressure for certain alpha, lambda combinations, below which quark stars cannot form, and above which the mass and radius are greater than or equal to those of a black hole. The mass-radius profiles of the stars increase with both increasing alpha and lambda, leading to a larger maximum mass point for a given parameter set. The theoretical aspects of 4D Einstein Gauss-Bonnet gravity are discussed, beginning with the field equations derived from the action. The variation with respect to the scalar phi yields an equation involving terms related to the curvature, the scalar's gradient, and its Laplacian. The variation with respect to the metric gives another set of equations, involving the Gauss-Bonnet tensor, curvature, and the scalar's gradient. These equations are used to derive a relationship between the stress-energy tensor and the scalar field, serving as a consistency check for solutions. The unified interacting quark matter equation of state is also discussed, describing compact stars in terms of deconfined quark degrees of freedom. This includes the pressure-density relationship for quark matter, highlighting the need for a more complex interacting quark matter equation of state to explain large compact star masses. Recent binary merger events have sparked interest in applying general relativity to the possibility of quark stars fitting observational constraints. Zhang and Mann explored this concept using a strongly interacting equation of state, inspired by theoretical developments on UDQM as the ground state of baryonic matter. Their framework condenses strong interaction effects into a single parameter lambda, providing a unified description of all strongly interacting phases of quark matter. The framework involves the free energy omega, which is written in a specific form encompassing terms for quark and electron chemical potentials, the gap parameter, and corrections from the finite strange quark mass. By deriving thermodynamic relations and reparameterizing the expression for lambda, the authors obtain equations for the quark number density, electron number density, and energy density. These equations are valid at low temperatures and provide a unified description of quark matter phases. This approach simplifies the problem of strongly interacting quark matter, allowing for a more comprehensive understanding of quark star properties and their potential to fit observational constraints. The unified framework and derived equations offer a significant step forward in modeling quark matter, enabling further exploration of its role in binary merger events. The pressure equation is derived by combining equations 15 and 10, incorporating the MIT bag constant, unified interaction strength lambda, and mass density ρ, r. This expression highlights how different parameter combinations can result in the same unified interaction strength lambda, leading to an equivalent equation of state. Dimensionless parameters are introduced through rescalings, 17, 18, and 20, resulting in the dimensionless EOs, 19. In the limit of zero interaction strength, the non-interacting EOs is recovered, while extreme positive interaction strength leads to a surface mass density reduction and maximizes the speed of sound in quark matter. The derived EOS is applicable only at low temperatures, as it originates from the grand potential, 10, without accounting for temperature effects. The Tolman-Oppenheimer-Volkoff equations, well established for modeling stellar structure within general relativity, require rederivation for quark stars under 4D Einstein Gauss-Bonnet gravity. Starting with a static, spherically symmetric metric ansatz in natural units, the derivation proceeds from the field equations. These lead to an equation for the scalar field, ensuring asymptotic flatness. The stress-energy tensor for quark matter is modeled as a perfect fluid, yielding equations for density and pressure. The derived equations, including those for gravitational mass, are discussed in detail, connecting seamlessly to previous pages for continuity. The modified Tolman-Oppenheimer-Volkoff (TOV) equations in the four-dimensional Einstein Gauss-Bonnet (4DEGB) gravity framework are derived, incorporating the 4DEGB coupling in the definition of gravitational mass. The resulting equations describe the pressure and mass gradients of a static, spherically symmetric gravitating body. The vacuum solution yields a constant mass, implying a cosmological constant, and the gravitational force is computed as, which is weaker than its Newtonian counterpart for alpha greater than 0. Rescaling the quantities using and yields the unitless equations, which can be solved numerically. In the limit alpha right pointing arrow 0, these equations reduce to the well-known TOV equations in general relativity, GR. The numerical solution is obtained by imposing the boundary conditions, where the star's surface radius r is defined as the radius at which the pressure vanishes, and the total mass m is defined as the mass at this radius. The gravitational force outside a spherical body is always attractive for alpha greater than 0, although weaker than in GR, and more attractive for alpha less than 0. The force vanishes at a smaller radius than the outer horizon of the corresponding black hole. The numerical solution of the TOV equations will provide insights into the behavior of compact stars in the 4DEGB gravity framework. The application of the four-dimensional Einstein Gauss-Bonnet (4DEGB) theory to compact stars is examined, with a focus on the behavior of the scalar field in both interior and exterior regions. In the interior, the scalar field equation is solved using a power series expansion around the origin, with a boundary condition ensuring regularity at the origin. This solution is then inserted into the gravitational field equation to determine the limiting behavior of the scalar field near the origin, crucial for maintaining regularity. The paper also explores observational constraints on the 4DEGB coupling constant, alpha, a dimensionless parameter characterizing the strength of the scalar field's interaction with matter. Current constraints bound alpha between 0 and 3.2, but preliminary calculations on recent gravitational wave data suggest potential tightening to 0 less than alpha less than 0.0032. This would imply that deviations from general relativity due to 4DEGB would only be detectable in extreme environments, such as the early universe or near extremely massive objects like black holes. Compact stars near the upper end of the mass gap are identified as ideal candidates for investigating 4DEGB effects, particularly if alpha is less than or equal to 0.0019. However, a comprehensive study of gravitational radiation in 4DEGB remains to be conducted. Therefore, the authors adopt the bound given by equation 40 for their analysis, acknowledging the need for further investigation into the implications of 4DEGB on compact stars. In this section, the authors numerically obtain the total quark star mass as a function of both total star radius and central density. The plots of mass versus radius are supplemented by the GR 4DEGB black hole horizon radii and the GR 4DEGB Bookdahl limits. The authors derive the outer horizon radius as a function of mass and the Gauss-Bonnet coupling constant, alpha. The Bookdahl bound, derived in the context of 4DEGB, ensures the pressure of the star remains positive and monotonically decreasing throughout, and for a given mass, the radius of the star must be larger than that of the outer horizon of a black hole of the same mass. Unlike in GR, there is no mass gap between a compact star and a black hole of the same radius in 4DEGB theory. The authors demonstrate that quark stars can have radii that are arbitrarily close to that of a black hole of the same mass, which is a novel feature of 4DEGB theory. The solutions to the 4DEGB TOV equations are presented for a positive coupling constant lambda is greater than or equal to 0. Equivalent to the condition xi squared a increment squared greater than xi squared bm squared s. As lambda increases, so does lambda. Figures 1 and 2 illustrate that both increasing alpha and increasing lambda expand the mass and radius of the star for the same central pressure, leading to larger maximum mass points. This occurs due to weaker gravitational attraction with alpha greater than 0 and a stiffer equation of state from strong interaction effects. For any given alpha, the m versus r curves move upward and rightward as lambda increases, and for any given lambda, the curves also move upward and rightward, with the upper part asymptoting to the Buchdahl horizon limit as alpha increases. Even for small alpha, stable solutions with smaller radii than GR Buchdahl and Schwarzschild black holes exist, as shown in Figure 3. The stability of these objects is an interesting subject for investigation. Findings are commensurate with those of Banerjee et al. 34, where increasing the coupling strength to higher curvature terms increases mass-radius profiles, yielding a larger local maximal mass point. This study varies the MIT bag constant, with a smaller BEF corresponding to larger Mr. profiles, correlating with a larger positive interaction strength. For sufficiently large alpha, lambda, no quark star solutions exist outside the black hole horizon, since pressure profiles smaller than criticality diverge to infinity with no real roots. This implies a well-defined central pressure, density at which P, R, equals P, 0, equals const, below which quark star solutions do not exist. The figure illustrates mass versus radius, central density curves for unified interacting quark stars, with varying 4DEGB coupling parameter lambda values. From blue to purple, the plots correspond to lambda values of 0, 0.5, 10, 100, and infinity, respectively. This analysis shows that as alpha and/or lambda increase, the mass and radius of a solution tend to increase. The solid and dashed black lines represent the Schwarzschild and Buchdahl limits within the 4DEGB theory, while their red counterparts mark the equivalent bounds in general relativity. These results highlight significant differences in the properties of unified interacting quark stars under different coupling conditions, providing insights into their behavior within the 4DEGB framework. The figure illustrates additional mass versus radius and central density curves for unified interacting quark stars when the parameter lambda is greater than 0. The curves are ordered from blue to purple, representing the values lambda equals 0, 0.5, 10, 100, and infinity, respectively. The solid and dashed black lines denote the 4DEGB equivalent of the Schwarzschild and Buchdahl limits, with their red counterparts marking equivalent bounds in general relativity. As the parameters alpha and lambda increase, the mass and radius of the solutions also increase. Notably, at certain combinations of alpha and lambda, solutions start at the black hole horizon, as shown in the lower panels. These solutions are unstable for all central pressure values. Quark stars with extremely small interaction strengths, represented by alpha equals 0.001, exhibit a range of solutions that yield stars smaller than the GR Buchdahl bound and the 2 Schwarzschild radius, as shown in Figure 3. These solutions venture into disallowed regions of parameter space, as demonstrated in Figure 2c. To better understand these quark stars, the authors approximate the pressure profile as a step function times a constant, allowing for an analytical solution to be derived. This solution provides insights into the minimum mass and radius of quark stars in the limit of vanishing interaction strength. The minimal mass solution is expressed as a function of the radius, with the corresponding radius determined by where the pressure derivative diverges. This research has significant implications for our understanding of quark star properties under different interaction strengths and their relationship to black holes and other astrophysical objects. The results shed light on how varying interaction strengths influence the mass, radius, and central density of quark stars, providing new insights into their parameter space. These findings are crucial for advancing our knowledge of quark stars and their role in the universe. In the analysis of the minimal mass point, its relation to the Buchdahl bound is paramount. Notably, this point is independent of the parameter alpha, yet plays a crucial role in determining the critical pressure. Focusing on the limiting cases, solutions for lambda right pointing arrow 0 and lambda right pointing arrow infinity sign are examined. The parameter alpha emerges as a vital component in these solutions, significantly influencing the outcome. Critically, these solutions intersect with the black hole horizon and the Buchdahl bound, resulting in unstable solutions for any central pressure above the critical value. This underscores the significance of the critical pressure threshold, beyond which no stable solutions exist. The implications of these findings on the parameter space are profound, as visualized in Figure 4. The interplay between the minimal mass point, the Buchdahl bound, and the parameter alpha is revealed, providing valuable insights into the complex dynamics at play. Figure 4 illustrates the critical pressure, P0 alpha, for a test value of lambda equals 0.1 and lambda greater than 0, defining three distinct regions in the parameter space. When the central pressure is fixed at P0 equals 0.15, the region from alpha equals 0 to the value that satisfies P0 alpha equals 0 exhibits valid, physical solutions at fixed PO. As alpha increases past this point, the red region emerges, characterized by parameter combinations with P0 greater than P0, resulting in unphysical radii inside the black hole horizon. The gray region, where P0 less than P0, exhibits radial pressure profiles that diverge to infinity. The boundary between the gray and red regions corresponds to solutions lying directly at the black hole horizon, which are included in the Mister plots as colored points. For lambda is less than or equal to 0, equivalent to the condition sheet 2a increment 2 less than sheet 2 bm2. Equation 55. The critical pressure diverges at alpha equals 9 pi, 32 lambda. This defines a critical relationship between the 4D Gauss-Bonnet coupling and the strong interaction parameter, where the central pressure must approach infinity for a valid quark star solution. The allowed range of interaction strengths inside the star varies based on the choice of coupling to the higher curvature term. Figures 6 and 7 illustrate the alpha-lambda combinations, chosen to keep the critical central pressure below P0 equals 10, allowing for a manageable comparison of results. The decrease in lambda, and increase in lambda, causes the mass and radius of the quark star to decrease, as expected. In the context of 4DEGB theory, this research paper explores the mass-radius relationship for compact stars, focusing on the effects of varying the interaction strength and Gauss-Bonnet coupling. The authors present graphical representations illustrating how changes in these parameters impact the maximum mass and radius of compact objects. When the interaction strength is positive, increasing the Gauss-Bonnet coupling leads to an increase in the maximum mass and radius of compact stars, along with a shift towards higher central densities. Conversely, when the interaction strength is negative, increasing the Gauss-Bonnet coupling results in a decrease in the maximum mass and radius, accompanied by a decrease in central densities. The paper also highlights regions where solutions violate the GR Buchdahl bounds and Schwarzschild radius, particularly for larger values of the Gauss-Bonnet coupling. This indicates that compact stars in the 4DEGB theory can exhibit properties not seen in general relativity. A stability analysis of these compact objects reveals that a necessary but insufficient condition for stability is dm, d rho c less than 0, corresponding to parts of the solution curves before maximum mass points are reached. However, a thorough analysis of the fundamental radial oscillation modes is required to fully understand the stability of these objects. The authors emphasize the importance of the causality condition, which states that the speed of sound must never exceed the speed of light. This condition is crucial for maintaining the physical validity of the solutions obtained within the 4DEGB theory. Overall, this section of the research paper provides valuable insights into the behavior of compact stars under varying parameters, shedding light on their potential properties and stability within the framework of the 4DEGB theory. The research paper provides a comprehensive analysis of mass radius and mass central density relations in the context of negative lambda values. It highlights the extreme sensitivity of critical pressure with respect to negative lambda, resulting in distinct sets of solutions for different alpha values. Increasing the value of lambda, which corresponds to decreasing alpha, leads to a suppression in both mass and radius, a logical extension of findings observed when lambda is positive. This research contributes to our understanding of the interplay between these key parameters and their implications for theoretical models. Figure 7 presents the mass radius and mass central density relationships for negative values of lambda, showcasing the extreme sensitivity of the critical pressure to negative lambda. This results in distinct sets of solutions for each value of alpha. The top row, A and B, corresponds to alpha equals 0.01, where the mass-radius relations are presented in A, and the mass-central density relations are shown in B. The curves demonstrate the effect of increasing lambda, decreasing lambda, on the suppression of mass and radius, consistent with the logical extension of the lambda greater than 0 results. The middle row, C and D, represents alpha equals 0.1, where the mass-radius and mass-central density relations are displayed in C and D, respectively. The plots exhibit a similar pattern of suppressed mass and radius with increasing lambda. The bottom row, E and F, corresponds to alpha equals 0.25, with the mass-radius relations in E and the mass-central density relations in F. Again, the curves illustrate the suppression of mass and radius as lambda increases. In all cases, the ratio lambda crit takes on the same set of values, namely 0, 1/25, 1/10, 1/2, and 1, respectively, from the blue to purple curves. This highlights the critical role of lambda in determining the mass-radius and mass-central density relationships. In the context of unified interacting quark stars, the sound speed plays a pivotal role in determining stability. The page under consideration delves into the relationship between sound speed and interaction strength, lambda, when pressure is held constant. The authors derive an expression for the sound speed, Cs, which converges to 1 from below as lambda increases for positive pressures. This result is significant because it indicates that the sound speed never exceeds the speed of light, thus adhering to the principles of special relativity. Furthermore, the effective adiabatic index, gamma f, is discussed as a key parameter for understanding the stability of adiabatic oscillations. Although a critical value for gamma f in the 4DEGB theory has not been explicitly derived, it is common practice to plot gamma relative to the Newtonian critical value. These indices are crucial in determining the stability of the star and its behavior under perturbations. The page highlights the importance of these indices in understanding the dynamics of unified interacting quark stars. Figure 9 illustrates the adiabatic index gamma f plotted over the surface of the star when alpha equals 0.0001 and lambda greater than 0. The different colored curves represent various central pressures, with the smallest central pressures having the largest gamma f at the origin. The black curve represents the Newtonian limit of 4/3. Table I presents the limits on the adiabatic index gamma. The table shows that gamma f approaches infinity as the pressure P, R, approaches infinity, and gamma f approaches 4/3 as P, R, approaches 0. The results also imply that gamma R equals 0 is greater than or equal to 4/3 in all cases, and gamma always diverges at the surface of the star. The equations in Table I are derived from the conditions that lim r right pointing arrow r gamma right pointing arrow infinity, and partial differential gamma, partial differential r greater than 0 due to the monotonically decreasing nature of the pressure profiles. The lower limit of gamma r right pointing arrow 0 is of particular interest, as it represents the starting point of the curves in Figure 9. The summary section recaps the main findings of the paper, which investigates the stellar structure of strongly interacting quark stars in the regularized 4D Einstein Gauss-Bonnet theory of gravity. The results show that, for both signs of the coupling lambda, even for small alpha, the quark star solutions asymptotically approach the 4DEGB black hole horizon radius, resulting in solutions with smaller radii than the Gr-Buchdahl-Schwarzschild limits. In general, larger alpha and lambda tend to reduce the radii of the quark star solutions. In the context of 4DEGB theory, the mass-radius profile of quark stars is examined, focusing on the effects of non-zero coupling on curvature gravity terms. A large negative lambda has an opposite effect, consistent with findings in the weak coupling regime. The research reveals the existence of quark stars below the Gr-Buchdahl bound and smaller than the 2m Schwarzschild radius, characterized by subluminal sound speed and an average effective adiabatic index above the Gr requirement. A critical central pressure is identified, below which quark star solutions do not exist, corresponding to radii equal to or smaller than the black hole of the same mass. Future avenues for research include investigating the stability properties of compact 4DEGB stars, the effects of charge on stellar structure, and the introduction of angular momentum. Einstein Gauss-Bonnet gravity is a theoretical framework that has garnered significant attention in the realm of astrophysics. Henniger et al. Have made notable contributions to this field by examining the d-right pointing arrow 4 limit of Gauss-Bonnet gravity, shedding light on its underlying theory and solutions. This work has profound implications for our understanding of spacetime and gravitational phenomena. In another vein, Zhang and Mann have proposed a unified interacting quark matter model, which carries far-reaching astrophysical implications. Their research explores the properties and behaviors of quark matter under various conditions, providing new insights into the nature of high-density astrophysical objects such as neutron stars and black holes. Ahmed et al. Have also contributed to the discourse with their concept of quintessential quartic quasitopological quartet, an innovative approach that integrates elements of quantum mechanics and general relativity. This novel framework aims to reconcile the discrepancies between these two fundamental theories, potentially paving the way for a more comprehensive understanding of the universe. Furthermore, Bueno and Cano's work on Einsteinian cubic gravity offers a fresh perspective on gravitational interactions. By introducing a cubic term in the curvature tensor, they have developed a new gravitational theory that could potentially explain certain observed phenomena without invoking dark matter or dark energy. These diverse investigations collectively underscore the richness and complexity of Einstein Gauss-Bonnet gravity, highlighting its potential to revolutionize our comprehension of spacetime, gravity, and the cosmos. As researchers continue to delve deeper into these theories, we may uncover novel insights that challenge our current understanding of the universe and inspire further exploration. Gravity theories, particularly the Einstein Gauss-Bonnet theory, have been extensively explored in recent research papers. A crucial aspect of these studies is the derivation of regularized field equations in 4 dimensions, which has far-reaching implications for our understanding of gravity. These field equations are essential for describing the behavior of gravity in various astrophysical contexts. Another area of focus is the d-right pointing arrow 2 limit of general relativity, which is closely related to Horndeski gravity. Researchers have investigated the connection between Horndeski gravity and Gauss-Bonnet theory, revealing intriguing insights into the nature of gravity. The papers also delve into observational constraints, examining the viability of these theories in light of empirical evidence. Furthermore, studies have explored the impact of these gravity theories on stellar structure and stability. By analyzing the behavior of stars in the context of Einstein Gauss-Bonnet theory and its variants, researchers have gained valuable insights into the internal dynamics of celestial bodies. The methodologies employed in these papers include advanced mathematical techniques, such as the use of tensor analysis and variational principles. The results have significant implications for our understanding of gravity, highlighting the importance of continued research in this area. Ultimately, these findings contribute to a deeper understanding of the fundamental forces governing our universe. Compact stars, comprising neutron stars and quark stars, have been extensively studied in the framework of Einstein Gauss-Bonnet gravity. Previous research has explored their properties, including mass, radius, and stability under various conditions. Notably, the Tolman-Oppenheimer-Volkoff equations have been employed to investigate the structure and stability of these celestial bodies. Recent studies have focused on the role of Gauss-Bonnet coupling in modifying the stellar structure, particularly in the high-density regime. For instance, it has been shown that the coupling can lead to a decrease in the maximum mass of neutron stars, accompanied by a simultaneous increase in their radii. This, in turn, affects their stability, as the compactness of the star is crucial in determining its ability to withstand gravitational collapse. Furthermore, the impact of Gauss-Bonnet gravity on the properties of quark stars has been examined. The results suggest that the inclusion of Gauss-Bonnet coupling can result in a softer equation of state, leading to a reduction in the maximum mass of quark stars. The review also highlights the significance of considering alternative theories of gravity, such as Einstein Gauss-Bonnet gravity, in understanding the behavior of compact stars. This is particularly important in the context of the neutron star mass-radius relation, which is crucial in constraining the equation of state of dense matter. The study underscores the need for further research into the properties of compact stars in the framework of Einstein Gauss-Bonnet gravity, particularly in the context of upcoming observational facilities that will provide high-precision data on these celestial bodies. In the context of quark star solutions, the concept of critical central pressure is explored. By numerically scanning through test values of central pressure Pc, the radius at which pressure vanishes, defining the stellar surface, is determined. Notably, for certain combinations of alpha and lambda, no quark star solutions exist below a critical central pressure Pcrad, where the pressure diverges towards infinity. To derive this critical pressure, the authors modify the equation of state by replacing P, R, with the constant Pcrad, yielding a modified differential equation for M, R, represented by equation A1. Integrating this equation results in equation A2, where the boundary condition M, 0, equals 0 implies C1 equals 0. Substituting equation A2 into the differential equation for P, R, and setting P, R, equals 0, the authors arrive at a condition corresponding to P, R, equals Pcrad, resulting in equation A3. This equation explicitly represents the critical central pressure Pcrad as a function of alpha and lambda. For fixed lambda greater than 0, the critical pressure takes the form shown in figure 11. When lambda equals 0, the critical pressure is Pcrad equals 4 pi alpha 3/18. For a given Al pair, only central pressures above Pcrad yield valid quark star solutions. If the critical pressure is negative, all positive central pressures result in valid solutions, and scanning can start from an arbitrarily small positive pressure. However, when alpha is sufficiently large, a threshold value of central pressure exists below which no solutions are possible. In the context of quark star models, the critical central pressure is a crucial parameter that defines the physical relevance of solutions. For positive lambda values, this pressure is determined by the intersection point of the energy density and pressure curves, marking the boundary of the parameter space where quark star solutions exist. Higher critical pressures correspond to larger masses which are more gravitationally attractive. The pressure profile for a typical quark star with a well-defined surface exhibits a monotonically decreasing pattern. However, when the central pressure equals the critical pressure, the pressure profile becomes flat, indicating no variation in pressure throughout the star. This scenario is demonstrated in figure 10b, where the central pressure is set to the critical value, resulting in a constant pressure profile. On the other hand, when lambda is negative, the critical pressure solution exhibits a divergence at a specific point, as shown in figure 13. Below this divergence point, the critical pressure is defined similarly to the positive lambda case, with only values above the curve being allowed. Past the divergence point, there are no quark star solutions for any central pressures, and thus the maximum alpha value is determined by the divergence point. This highlights the importance of understanding the interplay between alpha and lambda in determining the physical relevance of quark star models. The paper presents a detailed analysis of the critical pressure in a system as a function of the average value of alpha, denoted by alpha, when the parameter lambda, is greater than 0. Figure 11 illustrates the relationship between critical pressure and alpha for various values of lambda, specifically 0.1, 0.5, 1, 10, and 100. The darkest lines correspond to the smallest lambda, indicating that the critical pressure increases with decreasing lambda. In addition to the graphical representation, the authors also provide two scenarios for the radial pressure profile, Rp, R, in figure 12. These scenarios are differentiated by the initial pressure, P0, being either slightly below, figure 12a, or above, figure 12b, the critical pressure, Pcrad. This dichotomy highlights the distinct behaviors of the system on either side of criticality. The research demonstrates that the interplay between alpha and lambda significantly influences the critical pressure, suggesting that these parameters play crucial roles in determining the system's behavior near critical points. The findings have implications for understanding phase transitions and stability in various physical systems, particularly those where the interactions are modeled using the Lennard-Jones potential. Moreover, the paper's approach contributes to the ongoing discussion on the role of lambda in modifying the critical behavior of systems. By examining the relationship between alpha, lambda, and critical pressure, the authors provide new insights into the complex interplay between these parameters and their impact on the system's properties. Overall, this section of the paper offers a thorough examination of the critical pressure in a specific context, shedding light on the intricate relationships between key system parameters. The results and methodologies presented here are expected to resonate with researchers in the field of statistical physics and beyond, as they explore the intricate balance between different forces in complex systems. The final page of the research paper presents a detailed analysis of the critical pressure as a function of alpha, when lambda is less than 0. This is graphically represented in Figure 13, where the critical pressure is plotted for various values of lambda, specifically 0.1, 0.5, 1, 2, and 10, with the darkest lines corresponding to the smallest lambda. The mathematical functions past their discontinuity are omitted from the graph as they do not produce quark star solutions. Instead, the curves terminate at the point where the critical pressure diverges, marking the end of the solution space for these parameters. This study contributes to our understanding of the relationship between alpha and lambda in determining the critical pressure, which is crucial for understanding the behavior of quark stars under different conditions. By examining how changes in lambda affect the critical pressure, researchers can gain insights into the stability and properties of these celestial bodies. The use of these plots allows for a visual representation of the complex interplay between these variables, facilitating a deeper comprehension of the underlying physics. Furthermore, this analysis provides a foundation for future studies that may explore additional parameters or refine the current models to better capture the intricate dynamics of quark stars. In conclusion, this page serves as a culmination of the research paper's findings, offering a comprehensive visualization of the critical pressure as a function of alpha and lambda. It underscores the importance of continued exploration in this field to further elucidate the properties and behaviors of quark stars.